Hello students, let us start with next topic, coordinate system. Let us start with coordinate system. Okay, in which first theorem is the unique representation theorem. This theorem is called the unique representation theorem. Unique representation theorem. Okay. Let B is equals to B1, B2 and so on up to Bn be a basis of vector space V. This set is basis for vector space V, means what? B is linearly independent set and B spans V. Okay. Then for each V belongs to capital V, there exists a unique set of bases. There exists a unique set of scalars C1, C2 and so on up to Cn, such that V is equals to C1V1 plus C2V2 plus and so on plus CnBn. Okay. What does this theorem say? B is equals to set. This set be a basis of a vector space V. Then for each V belongs to V, there exists a unique set of scalars such that V is equals to C1B1 plus C2B2 plus and so on up to plus CnBn. Okay. Let us take definition. Let V be a vector space. Let V be a vector space. Let B is equals to set B1 and so on up to Bn be a basis of V. Let X is belongs to V. Then the coordinates of X relative to the basis V or B coordinates of X or the B coordinates of X are weight or scalars C1, C2 and so on up to Cn, such that X is equals to C1B1 plus C2B2 plus and so on up to CnBn. Okay. V be a vector space. B is equals to this set be a basis of V. Let X belongs to V. Then the coordinates of X relative to the basis, or we can say that B coordinates of X are weight or scalars C1, C2 such that X is equals to C1B1 plus C2B2 plus and so on CnBn. The coordinates of X relative to the basis V is nothing but the scalars such that X can be written as a linear combination of B1, B2 and so on up to Bn. Okay. In next line, write down notation. If C1, C2 and so on up to Cn are the B coordinates, B coordinates of X belongs to V, then vector in Rn, X coordinate, B coordinate of X belongs to V is equals to, or coordinate vector relative to the basis B is C1, C2 and so on up to Cn is the coordinate vector relative to B. Okay. This establishes the mapping. Establishes the mapping V to Rn defined as X is X2 coordinate vector of X relative to basis B. This is called the coordinate mapping. The coordinate mapping. This is called the coordinate mapping. Okay. Let us take examples for better understanding. Example is, let the set matrix 1 0 1 2 be a basis of R2, and coordinate vector of X relative to the basis B is equals to -2, 3. Okay. Find X. Okay. Here we have given coordinate vector of X relative to the basis, and also you have given basis. Then we have to find X. Okay. Coordinate vector of X relative to the basis is nothing but, here are two vectors, so that's why there exist two scalars C1 and C2, such that C1 into 1 0 plus actually we have given coordinate vector of X relative to the basis B. So this can be written, so X can be written as -2 into matrix 1 0 plus 3 into matrix 2 minus 3. Okay. X can be written as linear combination of these vectors. Okay. Now solve this. -2 0 plus -6 9. Okay. So we will get sorry, here is 3 into, this is 1, 2. So we will get here 3, 2. So our x is 1, 2. Okay. This is the method to find x when coordinate vector and bases are given. Let us take second example. If x belongs to R2 is given as matrix 1, 6 with respect to the standard basis of R2, then the coordinate vector of x, the coordinate vector of x is given by x is equals to, x is here we have given x 1 into matrix 1 0 plus 6 into matrix 0 1, which is equals to 1 e1 plus 6 e2. This and this are standard basis for R2. Okay. Solution here, coordinate vector of x relative to the basis B is matrix 1, 6. Okay. Here x is matrix 1, vector 1, 6 and coordinate vector of x relative to the basis B is also vector 1, 6, because here we have given standard basis. So write down one note. In general, if the given basis of Rn, the given basis of Rn is the standard basis, then the coordinate vector, coordinate vector of x belongs to Rn is itself. Students, keep in mind that if the basis of Rn is the standard basis, then the coordinate vector of x belongs to Rn is itself. Okay. Let us take one more example. Let B1 is equals to vector 1 minus 3, B2 is equals to 2 minus 5, x is equals to vector minus 2 plus 1. From the given information, find coordinate vector of x relative to the basis B. Okay. By definition, we write the corresponding vector equation. We write the corresponding vector equation as C1b1 plus C2b2 is equals to x, and this C1 C2 are nothing but the coordinate vector of x relative to the basis. Okay, therefore C1 into b1 1 minus 3 plus C2 into matrix 2 minus 5, which is equals to x is minus 2 1. Okay, solving the augmented matrix of the above linear system, so formed we get, solving the augmented matrix of above linear system so for we get matrix 1 2 minus 2 minus 3 minus 5 1, which is equivalent to 1 2 minus 2 0 1 minus 5. Okay, obtain this matrix. From this matrix, observe that C1 plus 2 C2 is equals to minus 2 and C2 is equals to minus 5. That implies C1 is equals to minus 2 into C2 is minus 5 minus 2. This is 10 minus 2 is equals to 8. So we will get C1 is equals to 8 and C2 is equals to 4. Therefore, coordinate vector of x relative to the basis B is equals to matrix or vector minus 5, 8 minus 5. This is coordinate vector of x relative to the basis B. Okay. In some problem, we have given coordinate vector of x relative to the basis, and bases are also given. In that case, we have to find x, and in this problem, we have given basis and x. We have to find coordinate vector of x relative to the basis x. Okay. It is very simple. Just use the definition of coordinate vector of x relative to the basis. Okay. Let us take next theorem. Let B is equals to B1, B2 and so on up to Bn be a basis for vector space, be a basis for vector space V. Then the coordinate mapping x2 coordinate vector of x relative to the basis B is 1 to 1 linear transformation is 1 to 1 linear transformation from V on to Rm, from V on to Rm. Okay. Let us take next topic, the dimension of a vector space. The dimension of a vector space. Okay. First of all, write down one theorem. if a vector space phi has a basis of n vectors, then every basis of V must contains exactly n vectors. What is theorem? If a vector space V has a basis of n vectors, then every basis of V must contains exactly n vectors. Now we will see definition of dimension of vector space V. Okay. The dimension of a vector space V, the dimension of a vector space V is the number of vectors in a basis for V, and it is denoted by dimension V. Dimension of vector space V is nothing but the number of vectors in basis. Okay. A vector space V is said to be finite dimensional. A vector space V is said to be finite dimensional if the vector space V is spanned by a finite set. Or basis is finite. A vector space is said to be finite dimensional if a vector space V is spanned by a finite set. That is what? If the basis of V consists of a finite number of vectors, then V is finite dimensional vector space. V is finite dimensional vector space. Then V is finite dimensional vector space. Okay. If V is not spanned by a finite set, then V is said to be infinite dimensional vector space. Okay. If V is spanned by finite set, then V is finite dimensional set. If V is not spanned by finite set, then V is said to be infinite dimensional. Or or basis of V consists of an infinite number of vectors, then we say that V is an infinite dimensional set. The dimension of zero vector space is singleton 0. Now we will write down the table for standard basis and dimension of a vector space. First column is vector spaces. Okay. Here standard basis, and last column is of dimension. Okay. First vector space is Rn. For Rn, standard bases are, we have already discussed, E1, E2 and so on up to En, and its dimension is n because its basis contains n elements. For P2, it is 1t square. Dimension is 3 because this basis contains 3 vectors. For Pn, standard bases are 1t square and so on up to t raised to n. Dimension is n plus 1. For singleton 0, standard basis, this has no basis and its dimension is 0. Okay. Next is the set of all 2 by 2 matrices. The set of all 2 by 2 matrices with real entries. For that, standard bases are M1, M2, M3, M4, where M1 is nothing but matrix 1 0 0 0, M2 is nothing but matrix 0 1 0 0, M3 is equals to matrix 0 0 1 0, and M4 is equals to matrix 0 0 0 1. And dimension of this vector space is 4 because in basis there are 4 vectors. Okay, these are the vector space. This is the standard basis and this is dimension. Okay. Next line, write down the basis theorem. Basis theorem. Let V be a vector space of dimension P, which is P is greater than or equal to 1. Any linearly independent set of exactly P elements in V automatically basis of V. Any set of exactly P elements that spans V is automatically a basis of V. This is very important theorem. We will make a vector space of dimension P where P is greater than or equal to 1. Any linearly independent set of exactly P element in V is automatically basis of V. And any set exactly P elements that spans V means what? Every vector in V can be written as a linear combination in vectors in this set. Is automatically a basis of V. Okay. Let's write down one note. The dimension of null space of A is the number of free variables in the equation Ax is equals to 0. And second is the dimension of column space. For dimension I will write only DIM. Dimension of column space is the number of pivot columns of A. These are very important results which will be useful for solving problems. Dimension of null space is the number of free variables in the equation Ax is equals to 0. And dimension of column space of A is the number of pivot columns of A. Okay. Let us take example. Example is find the dimensions of the null space of A. Find the dimensions of the null space of A and column space of A and column space of A of matrix A where A is equals to matrix minus 3, 6, minus 1, 1, minus 7, 1, minus 2, 2, 3, minus 1, 2, minus 4, 5, 8, minus 4. Okay. This is how to find dimension of the null space of A and column space of A. This matrix is given by row reduction of augmented matrix A0, we get an echelon form as follows. This is homework to you. Find this echelon form. Okay. 1 minus 2, 2, 3 minus 1, 0, 0, 1, 2 minus 2, 0. Here is again 0, 1 plus 2 minus 2, 0, 0, 0, 0, 0, 0. Okay. See here. This is the echelon form of this given matrix, and we have in just previous write down two notes that null space of A is nothing but the number of free variables in row echelon form. Here column 1 and 3 have leading 1, that's why they are not free variables. Column 2, 3 and 4 have no leading ones, therefore they are leading variables. Therefore there are 3 free variables. Say x2, x3, say x2, x4, x5. Therefore dimension of null space of A is equals to 3. Okay. Also there are two pivot columns corresponding echelon form. First and third column has leading one. Therefore, there are two pivot columns corresponding to echelon form. Therefore, dimension of column space of A is equals to 2. Okay, we will stop here. Thank you.